Data management, best management practices. Our primary objective in collecting data is to provide information about a resource's response to management. The primary outcome from our data collecting activities is that management decisions are informed by data. The information provided by data gathering activities needs to be both accurate and credible. Data gathering for monitoring a resource is the primary step that we take before determining whether the resource objective was achieved. So let's take a look at this in a little closer detail. Here we see a diagram of the adaptive management cycle, and it starts with a clearly stated management objective. The management is implemented, and then we need to monitor the resource in order to determine whether the objective was achieved. We determine the level of confidence and precision that we need in our estimate that we're going to get from monitoring, and so we develop a well-stated sampling objective. Combined, these help us determine what is the appropriate monitoring plan, and we have a well-designed and well-thought-out sampling design. We then go about the business of collecting data, analyzing and interpreting those data, and then using that to inform management. In this presentation, we're going to be focusing on the steps involved with data collection and management. Now, data management includes a series of stages and steps, starting with the collection activities, taking measurements or observations and recording those measurements. Data entry, transferring the data from the field format into a computer-based format so that we can then analyze those data. We often manipulate data or convert them in some way and then summarize and analyze before we get into the stage of interpretation, in which we report our findings. It's important that we always do a reality check when we are preparing to report our findings. Now, with all of these stages, there's many places where non-sampling errors can occur. And it's similar to a chain of events. The strongest chain is as strong as its weakest link. And we've all heard the saying, garbage in, garbage out. We work hard to collect data and to report our findings, and we want to make sure that our data gathering activities provide information that is both credible and accurate so that we're able to make well-informed management decisions. We put our names on these reports, and we want to make sure that the quality of information that goes into this entire process is as high as it can be. So in this presentation, we're going to be focusing on the best data management practices. It starts with preparing for data collection. That involves taking measurements and observations in the field. We need to clarify all ground rules for the methods that we're using, and it's important that those ground rules are also documented. Documentation is essential because we cannot be sure that when the next data collection activity occurs, that people will remember without having it written down what was done, or there may be new people involved and they need to know exactly what was done. It's also important that we carefully train observers and calibrate them so that we ensure that their observations and measurements are precise and similar. Recording data is also something that needs to be practiced. We prepare for this by using well-designed data sheets that are efficient and will facilitate the recording of data without error. And we need to train observers and recorders on how to record the data. We practice both taking measurements and observations and recording data in the field simultaneously, and then we review that process. We do this so that we can identify any problems that occur and address them so that they do not cause further problems down the road. Now, there are several types of problems that are associated with data collection. Main categories are inconsistent data recording, missing data, and poor handwriting. And we need to know how to deal with each one of those. So we're going to look at each of these in turn. First, there's the problem associated with inconsistent data recording. This can be best addressed by clarifying the terms and the formats that we use for writing data. So for example, if we are writing the names of species, we want to make sure that we use one set of terms. If we were in an area where we could be measuring black grama, we could use a species code BLGR for black grama, or BOER for the scientific name Bouteloua areophyta. Most commonly, researchers will choose to use the scientific name, and that's because it is less ambiguous than common names. It's important that this is agreed upon and followed by data recorders. We also want to clearly establish the terms and abbreviations that we use so that the recorders will be using one term and one abbreviation only. So for example, if we're measuring ground cover, we would want to establish whether we were using the word soil or the abbreviation S, and not the term bare ground or the abbreviation BG. The important thing is to be consistent. Now, how do we deal with missing data? This has to do with data that is missing on the form as it's written down in the field. We, first of all, need a set protocol for completing the forms. One thing that's very important is to ensure that on every single data sheet we record the metadata so that we do not have an unidentified data sheet, a sheet that has information on it but cannot be tied to the site or the sampling unit where it was collected is not valuable because it has no identity. So we make sure that we write the ID of the site, the sampling unit, the date, and the observer's names and other information that is important depending on your sampling objectives. We also need to have a procedure in place and practiced for indicating repeated data. And that's because blank cells tend to cause data entry problems. We can see in this data sheet on the left there are a lot of blank cells. And it's difficult to know if a blank cell in this case means that nothing was found there, or that the person who was recording these data, in this case the species code BORO, if they just meant that you assume that BORO was observed on every cell or on every observation until we got down to this lowest line 11 for where we could see a new species name. So for example, if you use a vertical line, in this case the vertical line indicates that on the first point of the transect BORO was observed, and the same is true for the second and the third, but then when we get to the fourth observation, there's a new species involved. So using a vertical line to indicate repeated data is important because then we know that it's not missing data because of a blank cell. Another common problem is poor handwriting. We need to first of all emphasize to our recorders that we are writing to communicate. Handwriting must be legible because sloppy letters and sloppy numbers can then cause data entry errors. In this case, we see on the left some of the numbers are fairly sloppy, and on the right they are more neatly written. And we can see highlighted here a couple of examples where the interpretation is different because of these handwriting errors. Instead of being interpreted as 1500 that we see over here, this number was interpreted as 1800. Similarly, instead of 420, this number was interpreted as 480. Now, where the error comes in, if we're looking at gap size in this case, is that the total gaps interpreted by this data set here is 718 centimeters, whereas when we look at the poorly written example, the total gap size was 968 centimeters. Now this is a difference of 250 centimeters on a 25-meter line. And that error is a non-sampling error, so it is not detectable and it affects the accuracy of our estimate. And it could have been avoided if the recorder was careful in their handwriting. There are additional things that we can do to ensure that we can avoid some data collection errors in the field. One is to check the data quality regularly. So to verify between the observer and the recorder which point we're on, or which quadrat or which transect is currently being measured, to have good communication. Another thing that we can do is to take photo points. First, this helps us with photo monitoring and documenting the conditions, but it also allows us to do a reality check when we get back to the lab and we're entering data in the computer and doing analysis. We can look at these photographs and know that the data that are on the data sheet associated with this particular transect, what the conditions looked like. We also want to make sure that we avoid worker fatigue, boredom, and physical stress. And so we can do this by trading jobs periodically, especially when the observers and the recorders are capable of doing both skill sets. We need to take frequent breaks, and we need to always be careful when we're in the field to be prepared for any kind of a situation and to make sure that safety first. Now, there are also a set of errors that are commonly associated with data entry. Some of the problems result from the fact that data entry is time consuming. We need to know what we can do in the situation of missing data, and also how to deal with typographical errors. First, we want to streamline for efficiency. Data entry is time consuming, so first of all we want to carefully design the electronic data sheet, usually at the same time that we've designed the data sheet that is being used in the field, whether it's electronic or paper. By having a good match between the formats of the data sheet, it first facilitates data transfer. You will have fewer mistakes and fewer omissions. It's also extremely important to include the metadata, notes, species codes, etc. that are the data, additional data that are recorded in the field need to be accommodated by the electronic data sheet. Oftentimes we will have a separate worksheet in our spreadsheet file just for notes or for species codes, but it's important to make sure that the information that identifies where the data came from and the conditions under which it was collected are retained with the data as they move through the data management process. We also need to have a set protocol for dealing with missing values. And this is because missing data happens. We're human, and recording errors do occur in the field. Also, we can have missing data if someone miscalculates the number of sampling units. So for example, if you had planned on taking measurements on 20 transects but lost count and only collected data from 19 transects, we need to know how to deal with that. We need to know how to indicate that data are missing, and also to make sure that we do not insert zeros for missing data. And we will now switch to a spreadsheet so that we can examine why that is. In this spreadsheet here, what we're looking at is a data set that was collected in the field. There were supposed to be 20 transects, but we can see that the data from this particular transect 15, is missing. And so in reality, we only have data from 19 transects that we can use. Now, there is a temptation to simply fill that row with zeros. And we want to look at why that is not a good idea. So I'm going to bring the analysis over here. Essentially, I've taken these two data sets and analyzed them. We've got the three different species, boar, arpu, and spiffle, and we've got two data sets. So we can see here, this analysis has the missing data, so the count is only 19, and this analysis has 20 observations, which was the original intent. But we can see that for all three of these species, that the value of the mean is changed by adding a zero to the data set. It's reduced, each one of these. And we can also see that our estimates of variability are affected. So both the standard error and the standard deviation are decreased by including a zero. It's important not to do this for a couple of reasons. It affects the mean and also our estimate of the variability, but it's also arbitrary. A zero means something. We could easily have inserted 25 or 30 or any other number. We don't know what the number would have been if transect 15 had actually been measured. But by adding a zero, you're saying something. Remember that zeros mean something. They mean nothing. They mean that nothing was there. Since nothing had been observed, we don't know, and it's important to leave this blank. And then just to note that instead of having a sample size of 20, as was intended, we instead have a sample size of 19. Now, when we're doing data entry, we also need to know what to do with typographical errors. So we need to cross-check our data to verify its accuracy. First of all, we compare the paper copy or the field copy to the electronic copy on the lab computer. We do this line by line and cell by cell. It can be time-consuming, but it helps us to find errors. Another thing that we can do is sort or filter our electronic data and look for abnormalities in the data, extreme values or outliers, and unusual formats. These help us to identify mistakes. And we're going to look at a couple examples using our spreadsheet. So here we're going to go to a new data set. This data set shows cover data that was collected on 30 transects, and there are multiple species. The data have already been totaled, so we have the total amount of plant cover that was contributed to by these 7 species. Okay, so with sorting, the first thing we want to do when we're sorting is we want to make sure that we grab all of the data. We don't want to separate the transect numbers from the data, so this would not be a correct way to start. We'd want to start here and select all of the data so that all of the information that goes with one observation, say the data that goes with one transect, stays together. I'm going to use the data sort feature, and I'm going to sort by the total cover. Now we know with plant cover it is bounded by values of 0 to 100. And so I'm going to sort this with going from largest to smallest and look for any outliers. So this is just a very quick way of checking to see if there's any numbers that don't seem normal. And we can see with these 3 transects, we have total cover values over 100. Now this is out of what would be expected. And so we should go back and look at the paper copy of the data and compare all of these values. We can see probably this 120 is a faulty value, but we don't know what the correct number is from the data sheet. So we want to just see that could be a data entry error, and we would want to correct that. Another thing that we can do is to filter data. So this can be done rather quickly by turning on the filter feature, which is located over here, and we'll try turning that filter feature on again. And what this allows us to do is to gather some information very quickly on all of the data in a particular column. So for example, this tells us that the observations observed in this column were 0, 1, and 6. And we can see here that we've got an abnormality. We've got a strange number. And so we'd want to then follow up on that. Now you could say, well, I can see just by looking at the data that this 100 is going to pop out at me, or this 116 is going to seem pretty strange. But if you had a very large data set, it would be difficult to see that. So you could see if you had hundreds of observations, how handy this filter feature is. Now when it comes to data analysis, there are also several practices that we can use to make sure that we are doing our analysis correctly. Sometimes we can make mistakes with mathematical conversions and also with when we sort or reorganize our data. And so again, we're going to go to our spreadsheet and look at a couple more examples. When we're using formulas, oftentimes we'll collect data in a certain format, such as the number of plants per transect that we see here. And we want to convert that to units that are more meaningful. So in this case, the transects were 15 meters squared, and we need to convert that data to the number of plants per meter squared and ultimately the number of plants per hectare. So what I do is I use a test formula. I know that I need a formula so that I can calculate the number of plants per transect, and that my transect was 15 meters squared. And so I would set up a formula where I tag the cell next to where I'm putting the formula, and then would divide by 15. I would do the same thing with the number of plants per hectare. I would take the number of plants per meter squared, and I know that there are 10,000 meters squared in a hectare. So I'm going to set up another formula, and I'm going to now tag this cell and multiply that by 10,000. Whoops, I have to multiply. Okay, multiply by 10,000. Okay, so now that's done. And then I'm going to test this formula with a number where I know it's going to come out the way that I wanted it to. So if I have a 15 meter squared transect and I had 15 plants per transect, then that would calculate or convert out to being 1 plant per meter squared and also 10,000 plants per hectare. If I had gotten a wrong number, testing something that I know how it's going to work out, I would then re-examine my formulas and make sure that they were okay, find out where the error was and fix them before I just assume that I'm using the correct formula. And now that I have this formula set up, I can copy it into place and copy it for all of my data. Now this is a good time to also talk a little bit about how to report data once the analysis has been done. So let's just very quickly here take an average of these values and take an average, and we're going to make sure that we use these values for this average. And we're going to talk about significant digits. Now, if we're talking about the number of plants per hectare, when we took these measurements, we did report, we took them in terms of individual units per transect, and it was a 15 meter squared transect. Now, the thing with spreadsheets and calculators is that they will give you lots and lots and lots of significant digits. It's important not to convert your values or not to round your values before you're done with all of your calculations. But Excel has just told us that we have 2,755.555556 plants per hectare. And that, you would never report that. You always need to remember what was the level of measurement precision that you had, which was to the nearest plant. In this case, we would translate this to 2,756 plants, or depending on what you would report, you could even report this as to the nearest 10, so 2,750 plants per hectare. You need to make sure that the number that you're using in your reporting is a credible number, because nothing is going to raise someone's eyebrows faster than telling them that they have that you were able to estimate the number of plants to 7 significant digits after a decimal point. Okay, so now another thing that we want to make sure is that you do rearrange your data very carefully and don't make any mistakes, such as sorting only parts of your data. So for example, if we only sorted this data, if we didn't select all of the data and then we sorted based on partial, we've now separated some of our data from the original, from the rest of the information that came with each one of the transects. Now, I'm going to use the Control Z key to get back to what it was originally. Oftentimes, what we will do is, after we've entered our data into a spreadsheet, when we start to manipulate it and we start to hunt and look for errors, we don't do that onto our original data sheet or electronic data sheet. Instead, make a copy of that data sheet, and then when you're manipulating, if you make a mistake, you haven't made all of the data worthless, and you don't have to go back and repeat all of that effort that you did before. So it's important to manage our data and rearrange carefully when we are manipulating data in the spreadsheet. And finally, with interpretation, it's always important to do a couple of reality checks. We want to look for red flags. Again, we're going to look at our spreadsheet very quickly on looking for red flags. Here we have a data set of cover data that are the number of hits per 50-meter transect, and we've got there's 20 transects, and we've got 3 species that were observed. We've already done the data analysis, and I'm going to pull that over now, and we can see that we've got mean values, standard error, standard deviation, etc. But it's always important to verify, is this what we were expecting? Now, I said that we had 20 transects, but if we look, we can see that the count data are only 18. So it must have been that when I was doing the data analysis that I didn't select all 20 rows. I only selected 18 of them. So it's this kind of a reality check that we can do to look for red flags to make sure that when we do our analysis and interpretation, again, we want to make sure that it's accurate and credible. And then finally, we do another reality check. We want to make sure that our output makes sense. So we looked for red flags, and then we want to make sure that our output makes sense. We should have a ballpark figure in mind. Not that we're able to walk out onto a field and say, oh, well, we've got 25% bare ground showing here, but instead just to know that it's approximate value. So remember, if we did some photo documentation, let's assume that this is what our photograph of the conditions were on the day that we collected data. If our data, the results of our data analysis indicate that we have perhaps this amount of bare ground showing, or even this amount of bare ground showing, yet we were expecting something on the order of what we see in this image here, that would raise a red flag that something is wrong somewhere, because the output simply doesn't make sense. Now, it may be possible, depending on the photograph, that there really was quite a bit of bare ground here in this image, but we want to make sure and go back and look at our data to be sure that the information that we're getting really reflects the data that was collected, and it's not reflecting a data entry error or a data management error. And then finally, it's important that we are sure that the data are going to be maintained. We want to maintain our records. We need to document the methods that are used and the ground rules that were applied. We also need to be very careful in data management with sufficient backup. This is especially important when we consider that over time different types of computer programs change, and we need to make sure that we've got both paper backup or electronic backup in multiple formats for both managing the data and for data storage. So finally, to conclude, information that we gather needs to be both accurate and credible. Data management presents many potential sources of non-sampling error. These types of errors affect the accuracy of our estimates, and they are not detectable statistically. We need to anticipate potential errors and take steps to avoid them. And we use best data management practices to reduce and eliminate avoidable errors.